So this talk is called MPI optimization. It's one of these sort of titles which is a bit disingenuous. I mean, you could have a talk called optimizing C programs or C++. It could be a million and one things. What I'm really going to talk about here are the common issues that people see, and they're often with point-to-point communication. So linking back to the discussion about how point-to-point communications work internally, how does that affect how real codes perform, and how can you maybe make sure that you aren't affected by some of the problems which quite commonly happen. So in general, the issue you have is you have a problem. You've written a solution in MPI. You have a large-scale MPI program, and you find that it doesn't scale. That the performance isn't what you expect. And this often happens when you go to a large machine for the first time. Often you can have issues which don't affect you on a few hundred processors, but then you go to a large scale machine and start running your application on thousands or even tens of thousands of processors, and you start to see issues. And these can be kind of generically divided up into four causes. One is lack of parallelism, one is load imbalance, one is synchronization, and one is communication cost. And I'll go through those, some in more detail than others in this talk. And don't worry, there aren't 38 slides. A lot of them are not relevant to this talk. So the first point is lack of parallelism. We want to do parallel computing. We want our program to go fast. But if all the MPI processes or processors you're using aren't working, then you're not going to get scalability. Tasks may be idle because only a subset of tasks are computing. And the classic thing here is one task only working or several. Work done only on task 0, or generically you have a split communicator and work is only done on task 0 of each communicator. But to be honest, the major issue here is that you have some piece of your calculation which is only done on one of the tasks, traditionally MPI task 0. And really the only cure is to redesign the algorithm to exploit more parallelism. So for example, a classic case people have is they have a calculation which is difficult to parallelize. So they bring all the data back to task 0, do the calculation, and then redistribute it. Now that may work on a few hundred processors, but it become a real bottleneck in a large number. So the problem here is that really the only thing to do is to redesign the algorithm. There is one slight caveat here, that often this overhead is due to I/O. So I mean, this course isn't going to touch I/O. It used to, but then it's too big a topic, so we have that in a separate course now. But if parallel I/O, if you do your I/O through a single process, often rank 0, so you do a gather, write, read, and a scatter, then that is not going to scale. And so for a whole bunch of reasons. And it is possible to do parallel I/O where at least not all, but a large number of processes are doing the I/O at the same time. And that is facilitated through the MPI I/O part of the MPI standard, or there are more modern libraries as well. But so there is some hope if your lack of parallelism is due to poor I/O performance. But other than that, you're really going to have to think about your algorithm. Load imbalance is another thing which is difficult to do. So okay, not all the tasks are working, but some are working harder than others. And this is a much harder problem. So in the shared variables model, OpenMP threaded programming, all your data is in one block of shared memory. So if you want to if you think that this task and an OpenMP, that would be a thread, has too much work, it can ask another thread to take the work, and all it has to okay, I'll have the work, and it just reads it. Okay. The problem with MPI or any distributed memory programming model is that you have to move the data. So not only do you have to say, I would like a new process to do the task which I'm currently responsible for, you actually have to give it the data. And that can actually take a lot of time. And it can require very, very significant algorithmic changes to get right. Large process accounts may be hard because a lot of the load balancing algorithms have a cost. So if you have P processes, then the load balancing algorithm itself can cost of order P time. And so that you get into this catch-22 situation that you have load imbalance, so your program is running slowly, but to address that load imbalance would require implementing an algorithm which makes your program go even slower. So again, load imbalance is a huge topic, and it is very, very tough to address. We will touch a bit on how to address it with hybrid MPI+OpenMP tomorrow, but the main thing is it is very tough, and again, it tends to hit you very quickly when you go to very large process counts. But again, unfortunately, that requires an algorithmic change. It's not, just changing the way you do MPI isn't going to help there. Actually, load imbalance can be quite difficult to detect or can hide. MPI, often people run a profiling routine and come back and see that their MPI program is spending a lot of time in certain routines, such as receives, waits, or collectives, blocking routines which are waiting for data. So a collective, if you do an all reduce, it requires all the processes to take place. So if one process calls it early or one process calls it late, it will wait. And often people will come to us and say, the all reduce on your computer is very slow. My program is spending 10 minutes in all reduce. Often that is not the function of all reduce. Often the time you spend in wait, receives, or collectives can actually be a symptom of a load imbalance. So if you have load imbalance, your process is going to be running at different speeds, and when they need to communicate, that one of your tasks is blocked because it's waiting for another task to enter the corresponding MPI call. So the tracing tools can show up load imbalance much more clearly, but it can be difficult. But you need to be careful. In a parallel program where you have multiple processes executing independently, what you mean by time, how much time did this spend doing this, cannot be an obvious answer. So, for example, the fact that one process spent a lot of time doing a calculation can actually show up as a lot of other processes spending a lot of time doing communication. But again, a good profiling tool would be able to distinguish between those two effects. But actually, synchronization is where. So in MPI, the reason actually that MPI is a relatively straightforward programming model is that synchronization is coupled to communication. In MPI, if I send a message, I don't have to worry if the receiving process is ready or not. If I receive a message, I don't have to worry if the incoming message is being posted or not. MPI will make either side, the sender or the receiver, wait until everything is okay. And so, but that means that communication implies synchronization. That's blocking sends and receives. Even if you do non-blocking comms, at some point you have to wait for that to complete, and that's a wait. And also collective comms are mostly synchronizing. So I would say that, again, this is quite a difficult issue, but I would say MPI barrier is almost never required for correctness. So if someone asks me so every synchronization costs time, an MPI barrier does nothing but synchronize. It doesn't do any useful computation. And it is difficult, they're not impossible, but difficult to come up with an MPI program where barrier is required for correctness. You often see people say MPI, they're going to do an all reduce. They'll say MPI barrier, wait for everyone to be ready, call the all reduce. You don't need the barrier. All the reduction collector operators do all the necessary synchronization. So the first thing I do if anyone gives me a program to optimize is that I take out the barriers. And if that makes the program incorrect, it was probably a buggy program to start with. So you may have barriers in there for timing. There are times when it can be useful to stop processes running ahead of each other to prevent kind of running out of resources. But really, if you've got a barrier in your program and it's not for, you need them for timing, because when you time the program, you want all the processes to start at the same point and line up at the starting line and then say go, like firing a gun in a 100 meters race. But I would take out the barriers. However, the use of blocking point communications can result in unnecessary synchronization. And later on, we'll investigate this in the benchmark. And what people often say is, well, it doesn't matter, okay? I have a program where I have a program where every process is doing the same amount of work. Okay, they're running in synchrony. They're doing the same amount of work, so that when they come to communicate, they'll all be communicating at the same time. However, what happens on the computer is actually very different from what you think may happen. So just because two processes have exactly the same amount of work to do does not mean they execute at the same speed. There's a lot of stuff going on, complicated stuff on a computer. For example, there can be random noise making your processes run at different times. Things like operating system interrupts. Every now and again, the operating system might wake up and process I/O requests or do various bits and pieces. So although you may imagine your process is running in lockstep, they're not, okay? So naturally, when you run lots of processes in a large parallel program, naturally the processes will end up running out of synchronization. So anytime you put in synchronization, you'll pay a cost, even if you've load balanced your problem. And this was discovered maybe 20 years ago when people first started on running more than a few thousand MPI processes, that the programs that were in principle load balanced, apologies, in practice were not load balanced because different processes doing the same thing did not. So modern computers are not deterministic in terms of performance, and that, so if you do, you should avoid all synchronization, unnecessary synchronization, because even if you think your program is load balanced, there will be load imbalance there from random noise effects, e.g., as I said, OS interrupts, things going on. So we're going to talk about a bit more detail here about communications, and start out with point-to-point, which is our go-to for all for understanding what MPI does. And I'm going to have some diagrams here as the kind of things which can happen. So first of all, you know, we've discussed this previously, that our model for sending a message is that there are two parameters which characterize the time taken to send a message. One is the latency, the startup cost, which is point-to-point communication typically incur a startup cost. Sending a 0-byte message takes a finite time, and that comprises two features. One is the cost of getting the data onto the network. So you know your node, each node will have a connection or multiple connections to the network, but there'll be some network interface card there, and getting the data from the processor, well, from the memory via the processor across the network interface card to the network itself takes some time. Okay, so not once it's in the network, it actually travels quite quickly. So in fact, so the costs are typically at the two ends, but there's two costs. One is that hardware cost, and the second one is software. MPI is a library. It's code. You have to execute code, and you know that takes time. Okay? MPI has to do quite a lot of checking and such like, and set up and managing queues. And so you know there's both hardware and software contributions to that latency. But anyway, even sending a 0-byte message takes a finite time, and as we saw from the ping pong exercise, even in ideal conditions going across the network, that is a matter of several microseconds, 4 or 5 microseconds. So the total time for sending a message is the latency plus the number of bytes you're sending times the time per byte. But I think it's easier to just characterize that as a bandwidth. So the time taken is the latency plus the number of bytes divided by some bandwidth. And as we saw, this was a few microseconds, and this is hopefully up in the many several gigabytes per second. But this simple model does tell you, well, the one very, very first thing, it's faster to send one large message versus many small ones. And there are two consequences of that. One is if you're doing reduction operations, do an all reduce of 2 doubles versus 2 all reduces of 1 double. An all reduce of 2 doubles will take exactly the same time as an all reduce of 1 double. All the time is in the processing and the coordination. The actually adding the numbers together is effectively sub-nanosecond. It has no impact at all. The other thing is if you're sending non-contiguous data, there is no single a standard MPI message, MPI send buff count data type, which gives you contiguous data. Do not send n messages of weight of 1 double. Okay, if you have non-contiguous data, you want to send a single message, and there are two ways of doing that. One is copy in, send, copy out, but the more elegant one is to use derived data types, and derived data types allow you to send strided data which is non-contiguous in memory. You may say, well, I have mixed data types. I have an all reduced, but it's not of a double, it's of double and integer. Well, derived data types here can be useful. So if you need to send combinations of data, then you can use derived data types to create a new object, which is those those two data types together. But this is really, it is faster to send one large message versus many small ones. So do a small number of reductions on large amounts of data, do a small number of message passing operations, each with a large amount of data. That's the number one optimization you can do. So assuming we're doing that, then we have a communication pattern, and our communication patterns can be relatively complicated. I mean, you may have the test application which we're going to use for measuring point-to-point communication is a 3D grid where every process exchanges messages with its 6 neighbors, up, down, left, right, forward, backwards. That's actually quite complicated, because if you map that onto onto a real program running on multiple nodes, some of the communications will be happening within processes in the same node. Some will be happening between processes which are quite close, have similar ranks, and some will be happening between ranks which have very different IDs, very different places in the network. So even conceptually simple communication structures can generate quite complicated communication patterns. So, and these communication patterns not just with our design, it's just literally who is talking to who. And so we trace there are certain trace analysis tools. I'll mention that. Well, I've got the Scalaska. I mention it not because I have any investment in it, because it's a free open source tool. It's freely available, and what it can do is it can trace it can monitor your code and produce a representation of what the communication patterns were. And there are a number of common patterns which happen, which can impact on performance. And you can identify these by hand, but actually things like Scalaska can actually look at your code and say, your program was spending a lot of time at this line here in this send or this receive. This looks to be like the problem of this particular communication pattern. So it will name them. So I'm going to go through the sort of standard naming convention for the problematic communications patterns. They're useful to know just for talking about them, but a tool like Scalaska may actually be able to say, use the same terminology. So the first one is a late sender, okay? If you issue a receive, a blocking receive, you say, I'm waiting for a message. As we saw in the quiz, you will wait until that message comes in. If the send happens late, then you have to wait, okay? So this is kind of obvious, but and this can be the symptom of load imbalance and such like. But if you issue a receive before the send happens, there's going to be a wait. And a standard profiling tool will show that up as a lot of time spent in the receive. However, that is likely a lot of it is waiting time. Now, some tools can distinguish the two. So if you're really lucky, your tool will say your program spent a lot of time in receive. Note that most of this time was in the synchronization, and only a small amount was in the actual receiving. It depends how good your tool is. But if you see a lot of time spent in receive, that is almost a certainty that is because you've got a late sender communications pattern. You're issuing receives before the corresponding send is being posted. The other one is a similar one, is out of order receives. So as I said, late senders may be the result of having the blocking receives in the wrong order. So you've got a receive here and a receive. This is touch, I should say. So these are different processes. And this is time going to the right. So what we're happening here is this process is issuing a receive from this guy, and it's waiting. But actually, the send comes from this guy first. But I'm not waiting for that guy, I'm waiting for this guy. And so this receive waits for that send, and then there's only then can I post this receive, which comes from that send. So the late send is maybe the result of having the blocking receives in the wrong order. So the naive thing you say here is, well, that's obvious. Instead of issuing a send to this process, issuing a receive to this process first, then a receive to this process, I swap them around. However, the problem in practice is that actually this lack of ordering can be a random effect. The next time you run your program, it might be the other way around. This might not be the optimal pattern. And so, I mean, if a sender is going, if you know what order the sends are coming in, then clearly you should issue the receives in the corresponding order. But in practice, that is often not the case. In practice, you don't actually know when they're coming in, and the difference in timing is due to random fluctuations, which you don't have any control over. But we'll come back to that later. But I think this important thing to point out, that if you impose an order, if you say, I want to receive from that person, then I want to receive from that person, if the sends don't happen in that order, you're going to have a wait. There's going to be an overhead, and so you should try and avoid that. The second one, well, the equivalent pattern on the other side is a late receiver. Okay, so if you see a lot of time spent in send, it could be that it's actually because the receive hasn't been posted. So this would only happen if the send was executed synchronously. If this send was an asynchronous send, then what would happen is at this point, the data would be copied into a buffer and the send would return. However, if send is synchronous, in other words, it's waiting for an acknowledgement, if send doesn't complete until the receive is posted, then you can get this late receiver pattern. And as we saw, the send can be synchronous for two reasons. Either you explicitly programmed it, you called MPI send. More likely, you called MPI send, but it was a large message. So if you called MPI send and the message was large, then the implementation would decide that it doesn't have enough space to buffer it, so it will become synchronous and wait for the receive to happen. So again, this would show up in your, if you did a profile, a runtime profile of your code, as a lot of time spent in send. However, again, most of that time is spent in synchronization as opposed to actual data transfer. Now, we don't actually see this. Yep, Sean?
Hi. So could you go back one slide, please?
Yeah, this one, yep.
If you decorated those sends and receives with the integer tag, would that would the correct send be picked up by the correct receive, or would it be could it still be in random order or something?
Oh, so actually, so maybe so what by out of order here, I mean out of order in time. Both of these programs are correct. Okay. So what I'm saying is that this is a receive from this process. Yeah. This is a receive from this process. The problem is you're issuing them in the sends are happening. Let's call this 0, 1, 2. The sends are happening process 1 first, process 0 first, and you're receiving 0, 1. Yeah. So all I'm saying is switch them around. So I should have made that clear. This is not about correctness. This is about the order that you issue in. So out of order meant. Sorry, I realise now I've used out of order in ordering into contexts. I'm talking here about ordering in time. So yes. So yeah. So I'm talking about both of these programs are correct. It's just that one of them incurs more of a delay than the other because the receives are not being posted in the same order in time as the sends. Does that make sense? I understand the confusion.
Yes,
I used ordering for a different for a different context in the previous lecture. Thanks for pointing that out.
Cool. Thank you.
Here, yeah, the send is yeah. So this is something I mentioned before, but it is important to reiterate. The right way to think about MPI is that it runs continuously. It's a universal postmaster, postmistress, postal service that delivers your messages. Okay. So people talk about what you think is that asynchronous or non-block communications happen in the background. If you, for example, let's say you post a buffered send, okay, it's copied into a buffer, and then at some later point, that data is transferred to the receiver. In your mind, you think of that magically happening in the background, okay? Therefore, your model is the communication and calculations overlap in time. This is not generally true. This would be nice if it were true, but it's not. And the reasons are transferring messages requires involvement of the process, the CPU, it's code, right? To transfer a message, you need to run code. Right? You need to do anything to do with message passing requires you running code on the CPU to do that. And the MPI library is single-threaded by default. We'll talk about multi-threading tomorrow, but you know, in general, the MPI library is single-threaded. And so if your program is running your code, doing some calculation, it is not possible for at the same time a message from this process to be being sent or received. Okay, your program is either running calculation code or it's in the MPI library when it could be doing message passing. It's not doing both at the same time. Now, conceptually, you think of them, you never think of it like that, but that is unfortunately true. So the only reason why MPI works at all, why MPI gives the illusion of running all the time, is, as I mentioned before, communication can only be processed when your program calls. So MPI treats calls to its library as manual interrupts. Whenever you call, if you actually look, if you download an open source implementation of MPI and look at MPI send, for example, it's a huge routine because basically it does a whole bunch of stuff before it does a lot. So if you call MPI send or any MPI routine, the first thing it does is, hooray, I'm now in the MPI library. I can actually keep things progressing. Are there any incoming messages, outgoing messages, sends, things to do? You can do all that bookkeeping, and then finally, I've cleaned up all the garbage. I can now actually do what you want to do. So that means that although you might think of MPI running continuously, it runs in fits and starts when it's in the MPI library. So, you know, MPI treat calls as manual interrupts, and we'll try to progress communication. So there's often a routine called, you know, progress, and that's the first thing any MPI routine will call the progress engine to keep things ticking over, matching outstanding sends and receives. So we often talk about non-blocking operations. If you issue a non-blocking send, your mental model is, well, it is correct that so you issue a non-blocking send, and then and then there's a receive at some point. Your mental model is that is happening continuously in the background. It's not true. More than likely, it was either sent at the start or at the end. Okay, it requires an MPI call to do it. It will not happen magically in the middle. So if you issue a non-blocking send, you tell MPI, please start sending this message, and I'll check later if it's been received or not. If there's an existing receive, it will be sent straight away. If there's not, it'll just be parked, and nothing can happen until the next MPI call. And that next MPI call could be totally unrelated to that non-blocking send. It could be the wait, in which case you might say, well, David's now waiting on this message. I've not sent it yet. I'll send it. Or it could be something complete. It could be an MPI all reduce. An MPI like, oh, okay, David's called null reduce. Before I do anything like that, I'll see if there's anything hanging around. Oh, here's a non-blocking send hanging around. Oh, the receives appear. Okay, I'll complete that now. So your mental model. So what I'm trying to say here is that there's an awful lot of talk about overlapping communication and calculation. In my experience, that almost never happens. However, that does not mean, but you should still use non-blocking communications, and I'll come back to why. So people often put non-blocking communications into their program goes faster, and they think it's because they're overlapping communication and calculation. It's not often, my opinion is it's often because they've reduced the synchronization, and we'll see why that is in the later slides. So here's late progress. This is a slightly complicated one, but let's get this right, because I always get this wrong. So you issue a non-blocking send, okay? But the implementation has, but there is no, so you've issued a non-blocking send to this guy, but the receive has not been posted yet, okay? So what happens is, MPI library says, I'd like to send a message to this guy, but they're not ready. I'll park it, okay? I'll not send it, and I return immediately, okay? So the message has not been sent yet, okay? Then you come along, and then the next time you enter the MPI library, the first thing MPI does is it checks, and it may notice now, oh, I can complete that send, and so the send happens. Okay. However, this MPI call may be completely unrelated to this and this. Okay. This is just the next MPI call you make allows MPI to check and complete things. And this is quite a weird one, but the send is delayed until the MPI library is re-entered by the sender. But that is not necessarily, this could be an MPI wait here, but it could be anything. Okay. And so this can cause delays between send and receive, which are kind of hard to diagnose, but fundamentally it's due to a late receiver. Okay. However, you would have thought that non-blocking communications would fix that, but it doesn't. It doesn't. So for example, let's imagine at this point. Sorry, I've lost my cursor. So I apologize, my laptop is not behaving itself today. Can you see my cursor on the screen? It disappeared for a bit. I'm concerned that my witterings won't make sense unless you can see it. Yeah, good, that's fine. Okay, so this guy posts an iSend. Okay, it sends it basically maybe sends a protocol message over to this guy, but it's not ready to, so it comes back. Yeah, this guy at this point issues a receive, sends a protocol message back to this guy, but this guy isn't ready to process it. It's only at this stage, when they're both on the line together, that it can progress this. So it is quite a subtle one, but I think the important point is that your mental model of MPI being a universal postal service runs all the time, that's the impression it gives, but the implementation is somewhat different. So late senders and late receivers may be avoided by more careful ordering of computation and communication. But as I said, in fact, often you just don't know what's going to happen, who's going to be late or who's going to be early. These patterns can occur because of random noise in the operating system. So the reason you get random, not all tasks take the same time to do the same computation. Not all messages of the same length take the same time to arrive. So even because you may think your application is load balanced, but if two processes talking to each other on the same node versus two processes talking to each other a long distance on the network will take different times. So your program will then become out of synchronization. And so I think the one message I'd have here, and hopefully this is borne out in the exercise, is to avoid delays, you should use all non-blocking comms entirely. I think a little knowledge is a dangerous thing here. A lot of people learn send receive as a way of doing point-to-point exchange, and they program everything up with send receive. That is not, that's one of the patterns in my benchmark, but I think really if you do everything in a non-blocking way, then I'll come back to why it really is the best way of doing it. And as we saw when we talked about the point-to-point, it's always best to post the receives first, because if a receive is posted and a send comes in, it can match straight away. So it's always better if you can post the receives as early as possible. But the major thing is, in performance critical parts of your program, use non-blocking communications for everything. Not elsewhere. Okay, people then overuse. People use it's only in the performance critical part of your program you should bother worrying about non-blocking communications. Are one of the few places in MPI where you'll hit subtle synchronization issues, because you have to remember that this buffer is potentially in transit from process A to process B and not read or write to it. So that's unusual. So I'm going to use halo swapping as an example, and this is in the benchmark as well. So I've got a halo swapping where I have a standard stencil computation. So my computation is computing a new array as a function of an old one, and it's a standard up, down, left, right, minus the middle type thing. This actually comes from an example I use on my MPI program. But the important point is you have an update. So you have a problem size of m by n. Here m and n are both 1, 2, 3, 4, 5, 6. Okay. We have an update or an algorithm which requires data from the 4 nearest neighbors. It's a 5-point stencil, and therefore what we've done is the standard thing is we've extended the local domain not to be from 1 to n and 1 to m, but to be from 0 to m plus 1. So there's a typo here, apologies. One of these should be n. That's apologies about that. That should be n+1. M and n are the same here, but I've made a typo. Apologies. And so what you do is you identify 3 regions of the date of the problem. There's this interior region which can be updated independently of the boundaries. There's the boundary region which you need to send to your neighbors, and there's the halo region, which is the data you receive from your neighbors. So these 3: the core region, which doesn't depend on any data from your other processes; the boundary region, which is the data you send to for other processes, and that data is received into the halo region. So what we typically do is we swap the data, and then we can execute this loop identical to the serial loop, because if I'm executing this, look at this point here, I have j minus 1, I plus 1, but j plus 1, I minus 1. That data has been copied incorrectly. Okay, so that's normal halo swapping. Okay. How are we going to do that? Well, the point is here that we are going to receive data from 4 neighbors and send data to 4 neighbors. We do not know a priori who is going to be ready first. It's because of the different iterations, different times of day, different days of the week, different processes will be ready earlier or later. And so the naive thing to do is to loop over the sources, receive the value from particular source, and to basically receive in some order: receive up, receive down, receive right. That is not a good thing to do, okay? Because you're imposing an order. So you might say, first of all, okay, I want to receive data from the process up from me. Well, maybe it's the process down which has already sent the data, and you'd be better to receive from them, but you don't know what the ordering is. So what you really ought to do is to loop over the source and receive the value from any source. Okay. Now, it's not a good idea to use wildcarding here, MPI any source. What you should really do is to use non-blocking communications. So what you should do is issue a non-blocking receive for each source and issue a single wait all. So my advice is just issue all the non-blocking receives at once, and then wait on all of them at the same time. So so do not impose unnecessary. Loop over the directions. Do a send up. You want to do send up, receive down, receive up. What you should do is do an I send up, or I receive down, and I send down, and I receive up. And this is basically, when I say loop over directions, I mean X and Y, because in each direction you have 2 sends and 2 receives. And then, so what we're doing here is we're not assuming anything about the ordering. Apologies, my laptop is not happy today. Yeah, there we are. So we're basically we issue all the communications, I send, I receive. So we issue them all, and then we do a wait all. So what this does is, what we should not do, if some people do this, then they wait individually, wait on communication 1, then you're imposing an ordering. What's happening here is you're telling MPI, I want to do all these communications, lots and lots of communications, and then you're waiting on all of them. So MPI can sit there and basically it's then waiting on all the communications to complete, and it can basically resolve them as and when they come in. You're giving MPI complete freedom to resolve the sends and receives as they come in. Okay, so you're not prescribing any ordering in which they're initiated, really, and any ordering in which they're completed. And so that pattern, do everything non-blocking and then do a wait all, is what I would recommend for a standard programming. And it definitely, we'll see even a simple benchmark program, it does show improved performance. Now, of course, you can then attempt to attempt to overlap communications calculation. You may want so the strategy here is we start all the non-blocking sends and receives. So we initiate communications for all this data here. While that is happening, well, logically while it's happening. We then apply our algorithm to the core region. So we update all of these points here. Then we wait for completion of the non-blocking sends and receives. And then we complete the calculation at the 4 edges. So we complete the calculation here, 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 and here. Now, in your mind, that means that these non-blocking sends and receives can happen in the background, overlapped with this calculation. I am dubious as to whether that happens in practice. There are benchmarks you can download which will measure how much your implementation of MPI overlaps communications and computation. I would say if you're going to do this, keep the simple version, So, because there's more bookkeeping here, this may overlapping communications and calculation may or may not improve your time to solution. It may slow it down. So if you do implement this, make sure you keep a simple version which doesn't overlap and always compare the two. But I would say this is my number one advice. Issue all your communications as non-blocking communications and then do a wait on all the requests. You can do these with persistent communications. Is there a question here? Fine. Maybe that was just somebody coming in. You can use persistent communications. However, as I said, this is again benchmarked in the benchmark, measured in the benchmark, I should say. I don't think this, here you, the standard message issue, I receive, I send, and then you do a wait all. The persistent communications, you initialize them, and then your iteration was MPI start all, MPI wait all. Again, I don't think there's much advantage to this, but you may like it. So you may think that this code here is more elegant than this. It's up to you. Again, as I said, it's very, very important that with persistent communications, message ordering is not guaranteed. The rationale is that MPI should be allowed to issue them when you do MPI start all, MPI should be allowed to start them in the order in which it prefers. And so you may need to use tags to guarantee correct message matching. So neighborhood collectives I will cover in more detail later on, but the standard collectives, and I just mentioned them here, the standard collectives apply to a whole communicator. So an MPI all gather collects data from all P processes, and MPI bcast broadcast to all processes. Neighborhood collectives apply to neighboring processes. So MPI neighbor all gather collects data from your neighbors. What does neighbors mean here? It means the people that are closest to you in the Cartesian topology, which you have created. So so in a regular grid, you might create it with MPI cart create. And I mentioned this here because although I'm not describing it in detail, it is part of the benchmark. I'll describe this communications operation, neighborhood collectives, in the final lecture of today. You can also use this for unstructured problems using a graph topology, and I have used this in a real program. I had an unstructured problem. It was a finite element problem, and I was able to do the halo swapping in an unstructured problem with a single call to MPI all-to-all, neighbor all-to-all, apologies. That does require a lot of setup, but it is quite elegant. So MPI neighbor all-to-all can implement halo swapping in a single call. Collectives, I'll not go into these in any detail. I think these are fairly obvious. That you can have, if you have broadcast where a root process is the origin of the data. If the root process is late, then you will see a lot of time. But to be honest, what you often see this in practice, because your program may say, if rank equals 0, read in data, then broadcast it. Basically, everyone except for rank 0 calls the broadcast straight away. Rank 0 is doing the I/O, the input, and then it calls it later. So it may not be a problem. But so if you ever have a communications routine, so a collective routine which has a root, such as broadcast or scatter, if that root enters late, then it will eat up time. Reduce is the same. If you do an early reduce, but only the root is calling it, but the other processes aren't ready, you'll get a lot of time in it. Again, all-to-all again. If you have an all-to-all program, if they don't all enter it at the same time, then there will be a lot of time spent in synchronization. But again, all of these are normally time spent in these routines is normally a symptom of load imbalance. So collectors are hopefully well optimized. You should never ever look up a manual and implement an all gather or an all-to-all yourself. However, they are expensive and they force synchronization of tasks. So you should reduce their use as far as possible. So call one collective with a large amount of data, rather than lots of collectives. There can be, so for example, you may have an iterative method. Often you have a reduction operation. You'll be looking for some error tolerance. I want to stop this calculation when the error is less than 10 to the minus 5. If that reduction operation is expensive, it may be worth just checking every 10 iterations. Okay? That may mean you do 9 more iterations than you need, but that may be faster overall than checking every time. Your immediate idea here is, well, let's issue these, just like I said, for out of order sends and receives, issue non-blocking sends and receives. Here you may say, well, surely for collectives, non-blocking collectives is the answer. I can go and I have found them not particularly useful in practice. I could discuss this later, but I'm not a fan. You can try them, but I really am not a fan of them. I don't think they're particularly useful. They ought to be, but they just don't turn out to be. So general advice, try to avoid imposing any non-essential message ordering. When the messages are actually sent can change on every time you run the program. So try to allow MPI to deal with the messages as they happen, which means issue all sends and receives as non-blocking. Issue the receives as early as possible. That's a bit of a gilded, gold plating, but you might as well. And complete them with a single wait tool. You're saying MPI, I want you to wait for all these communications to finish, so MPI can then complete them and match them up as they come in. You can set up persistent comms, but I don't see any particular performance benefit in that. Or use neighbourhood collectives. Again, they give you probably the same performance as a completely non-blocking approach. But avoid unnecessary collective calls. I say by aggregation, but do you really need any of those barriers? Is probably the first thing I would always say. So sort of the summary here, we've talked about lack of parallels and load imbalance, but really those are things which are algorithmic. The synchronization of the communication, the real message here is to do non-blocking communications. So slightly over time, apologies, I started 10 minutes later because of my AV problems. What I will do is I'll just very briefly show you the exercise. So if I go to the correct page, I've lost all my bookmarks by having to log off. I'm going to have to go back. Okay, so I'll share this. So this right. So the 3D headers-wide benchmark is this README. So I would say you could download the code directly to ARCHER2 and run the head. So I will just go to. This is actually on. But I would say that what the Halo benchmark does is it sets up a 3D array of processes and swaps Halo data up and down in all 3 directions. So this is indicative, hopefully, of a real MPI application, a fairly simple one. But it's a lot more realistic than it's a lot more realistic than a ping pong. Actually, sorry, have I? Sorry. Sorry, my laptop is having a bad day. Apologies for this. It's not. Okay. It's not doing the right thing. I'm sorry. It's not. Apologies. Are you seeing a website? Are you seeing garbage? Apologies. Something is going wrong. Something wrong with the.
We're seeing the what's this? You know, the collab website.
Okay, sort of collapsing in on itself. Okay.
Yeah.
So that shouldn't be happening. So I am actually picking share. Okay, no, I wasn't. I was being an idiot. Sorry, I'm fine. Okay, does that look better? Yes. Hopefully, yeah. So sorry. So this is my. Unusually for me, I put it on GitHub. You can get the Halo bench here. So as it says here, this code sets up a 3D array of process swaps in all three directions using a number of different methods. You can change the size of the buffers, and the approaches it uses are, I basically try to implement every approach I've ever seen anyone do for Halo swapping. So pairwise swapping each dimension in turn using MPI send receive. Another option that people do is that they split their processes into odd and even blocks, and half the processes send and half receive, then you switch round and then receive. So that uses blocking communications all the time. Then you loop over dimensions and do pairwise. You swap up, down, left, right, forward, backs in turn, and there are 3 ways of doing that. I send, receive, and wait. I receive, send, and wait, or I receive, I send, and wait all on both of them. These are all of these 1, 2, 3, 4, 5 approaches impose an order. Each dimension in turn, each dimension in turn, each dimension in turn, each one. So all of these have some ordering, and as I keep saying, I think that's a bad idea. These 3 final methods have no ordering. Non-blocking comes in all dimensions and directions at once, which is what I would recommend. I receive, I send, and wait all. The same thing with persistence, and the same thing with neighborhood collectives. I haven't explained how they work, but they're in there. There used to be a bug in the implementation of neighborhood collectives, and the code does a consistency check. So just before I will show you the code. The code is really quite simple. It's for Tran for historical reasons, but I think the only parameters you might want to change are nbuff is the size of each halo. So here we're sending 10K messages, and nrep is how many times it repeats it, and you want to modify these so you get a reasonable runtime. I think as it is, it takes about a second or so to do each halo swap, and it basically just calls all of these things. So hopefully you should be able to, and there is an ARCHER2 .job which runs this on 8 nodes. So I would actually recommend, or you can run this in the short queue. If that doesn't work, you can actually use the reservation. But 8 nodes is a read. So this is running on about 1,000 processes. So it'd be useful if people could compile and run that benchmark. It should compile out the box with make minus mesh make file ARCHER2 S batch. That should work. So if someone maybe I need to just get myself a glass of water, but could someone confirm I have a habit of making my repos private rather than public. I just want to check that repo is clonable. And I did check this myself, but you never quite know until. Okay, right, brilliant. So yeah, brilliant. Okay, that's really good. Thanks. So I will just be gone for 5 minutes to get myself up. But fingers crossed that this illustrates the desired effect. It would be very interesting if people have access to other platforms that they run this benchmark on their platform, because your mileage may vary. You may get different results on different platforms depending on your network, depending on your MPI implementation. But on ARCHER2, I think I understand we get a reasonably consistent picture. I will actually, and I'll run one as well. The reservation is for, I think it's for, it'd be nice to run a really big job. I think you can maybe run on up to, if you use the reservation, I think you can run on up to 24, maybe even 32 nodes. I can't quite remember, but I don't have that. But if you try, if you submit a job that's too big to the reservation, it will just say too big. But it would be good if you use the reservation. I think you can run on. I think you can run on up to. Okay, so maybe try running on a larger number of processes. So good, maybe try the reservation, Sebi, and see if you can maybe do it on 24 nodes. 24 nodes. So we saw that. So let's have a look. So hopefully you can see my screen now. Fine. So I ran the benchmark straight out of the box. Hopefully you see those as well. And we got. So do you want to mute yourself now? Sorry, I think it's your audio is still coming through. Is that okay?
Yeah, that's okay.
Yeah. So just mute your microphone. That's fine. So this was out the box, and it was doing 10,000 doubles. Yeah. Now normally that would be way above the eager limit. However, on ARCHER2 it's below. But if we look at this, we can see that where's my window? We can see that basically the send receive is the worst at 300 megabytes per second. The rest are sort of about 400, a bit less. But these three here are basically the best. So what I said was, what I guessed was that all non-blocking is the best. It's identical to the neighborhood collective. So I'm sure the neighborhood collective is doing nothing but that. And this is basically within the same. So all these three methods at the bottom do not impose an ordering. Okay, so that's quite good, and that works quite well. So the difference is maybe 20%, 15-20% in the time. I also did run a version where I actually did a much bigger value. So I did 100,000 doubles, and that is way above the eager limit. And you can see here that send receive is very bad actually, for reasons I don't know if I quite understand. But send receive is by far, and a lot of people use that's poor. 320 megabytes per second. The rest are 360, 402, 401. But again, by far the best are these ones here. And I was also going to run one which was maybe do 1,000 and do 10,000 repetitions. So just go to a really small. So sorry about those warnings. The Cray compiler has suddenly become very strict about Fortran. I would normally not distribute a program which had warnings in it, but this has appeared very recently. It's something to do with the modules. I'm running here on 24 nodes actually. You maybe didn't see that. So this is actually a very small message size, but corresponding a lot of. Okay. So let's see if this gives a different result. So here we are. We have each header contains 1,000 doubles, which is relatively small. And again, we're getting send receive is 320. Now we're getting similar numbers, where the So the best is always I send, I receive, I send, or neighborhood collectives. But this, this is showing you that with a relatively small amount of programming, you get a reasonably significant benefit. So hopefully that was a useful. Yes. So
Yeah.
the persistent start with that Sebi says that's I don't really understand that. There is no reason why it should do that. Oh, no, I think there is a reason. There is a reason. No, there isn't a reason. I can't think of a reason why that would be. That's a very good point, Sebi. I noticed that is something which is strange. If we look at the code, oh no, it's Halo swap.f90 that actually has them. So okay. So I am okay. So that's okay. That's actually identified. That's a bug in my benchmark. Well spotted. I am including the time for the initialization. Oh no, wait a second. No, that's just that can't be it. That's a tiny little overhead. Maybe it's possible. I can't believe it. What was your value of nrep roughly? I don't know. I can't believe that this setup cost here is significant because it's of order. This is 10 or 20 loops, whereas this is thousands here. But maybe it is. I will look at that. I will look at that. It could be I'm timing. It could be that the setup cost is high. I wouldn't have expected that. I can check that. That's a good point. That's a good point. But I think. Can you send me? Can you post what your parameters were, Sebi? Sorry, I apologize, I'm pronouncing your name wrong. Can you post the parameters? You say small buffer size. Can you post those parameters here? What buffer size you used? And I will. That's a very good. That's interesting. I don't know if that's a function of my benchmark or if it's a real effect. Buff size did. Okay, that's fine. Okay, that's useful. I will have a look. Okay, I know why. So my assumption was that this nrep was so high. I would say nrep. How long did each Halo swap take? How many seconds, roughly? In actual seconds, as opposed to. I mean, what was the actual time that it said? Okay, so that time is so small that this setup cost will be significant. So if the time is not near a second, set nrep to be 100 times bigger. And then see what we get. I have to go now. But that'll be interesting. So I assumed that the setup cost would be insignificant, but that is only true if you have a very large nrep. So make nrep 100 times bigger, so your seconds will be 100 times larger, and I think then you will see that. So at the moment, it is a slight bug in my benchmark. I'm assuming that the Halo swapping is taking an order a second, meaning the setup cost is insignificant. But for small nrep, that's not true. So okay, so let's get back at. Can we do maybe give you half an hour back at? We'll say at 5 past. Give us 16:05, and see you then. Okay, but that's I think it's a combination of my benchmark not being as robust as it should be. Does that make sense? I should have a separate setup. Okay, see you all at 10 past. Great, you can. So I thought it would be useful to maybe actually. I apologize if many of you aren't Fortran programmers, but hopefully Fortran is reasonably readable. So what I was going to do is kind of show you what the problem is. So I'll actually stop sharing this. This is the wrong thing to do. And share. Right. So some of you may be familiar with process topologies, but if you're not, I wanted to show you how they work, and then why the way they were used in early versions of MPI were not particularly what's the word? Didn't take them to their full extent. So what I have is I want to arrange here I have a bunch of processes in this program, and I want to arrange them in a 3D grid. And the reason I want to do that is I want the processes to be in a 3D grid, and I want to find out my neighbors up, down, left, right, forward, and backwards in those X, Y, Z, or whatever 1, 2, 3 dimensions. And that's a very standard thing you want to do in a code. You want to, that'd be a standard, fairly standard regular 3D code. You split your cubic domain if you've got a 3D volume up into a block, and you want to do halo swapping. So you want to arrange your processes into a 3D grid and find out who the neighbors are. So the way I do that here is I create a 3D topology. So there's 2 steps to that. MPI dims create basically tells MPI, I've got this number of processes, could you arrange them in a 3D grid? So I won't, but you're saying, look, I've got 1,000 processes, could you arrange them in a 3D grid? It might say, yeah, I think that 16 by 16 by 4 or 16 by 8 by 8 makes sense. So it will suggest a decomposition. And having done that, we can then create the 3D topology, which is called a Cartesian topology. And so so MPI cart create tells MPI, I've got this communicator which is com world, and I want to tell MPI that these processes are now in a 3D grid. And what you pass at these arguments, and you're telling, and basically you get out a Cartesian communicator. So you get out a Cartesian communicator, which then is the same, has the same processes as this communicator, which was MPI com world, but the processes are now arranged in a 3D grid. Having done that, you can ask MPI, who are my neighbors up, down, left, and right? And that's done with a routine called, okay, so if we look at the halo send receive, for example, a halo swap, if I look at one of these, I get, well, I've actually hidden this all away a bit, but so this isn't maybe as useful as it could be, sorry. But what I do is I use the MPI cart shift. So having created this Cartesian topology, where I've told MPI the processes are in a 3D grid, I can then find out the neighbors by using something called cart shift. And what cart shift does, it says in this 3D topology, which is a Cartesian grid of processes in 3 dimensions, who are my neighbors in each dimension? So I loop over all the dimensions and say, who are my neighbors up and down in each dimension? Having done that, I can then do point-to-point send and receive. Well, that all seems rather baroque. Basically, you're saying you have this, you want to send and receive messages to all your neighbors. There used to be no routine which said, please send and receive messages to all my neighbors. You had to individually say to MPI, who is my neighbor in each direction, and then issue point-to-point send and receive. And that seemed to be a bit of a waste. However, there is this new routine called neighborhood, the neighborhood collectives, which Halo's Halo red black, Halo, which I can find here. There we are. And you can see, so that for let's make this window a bit bigger. You can see that, for example, for the non-blocking send receive, this is what it looks like. Yeah, I have to loop over all the dimensions and the directions, and I have to issue a separate iReceive and an iSend. So I have to issue all the iReceives and iSends one by one for all the dimensions. There's quite a lot of code here, okay? And the only thing that the Cartesian topology has done for me is computed the neighbors. So who I'm sending and receiving from. Okay, if you look further down, the send receive call just does this. MPI neighbor all to all, send buffer and MPI position receive by. That does all of that for you. Now, there is a bit of setup to do, but these neighborhood collectives are a very, very powerful way of expressing nearest neighbor communications here in a regular grid. But if you say, well, I'm an engineer, I have unstructured meshes, I have undirected graphs rather than Cartesian topologies for my communications, then you can do that as well. So that was really, hopefully that was just to show you how terse the syntax is potentially. So I will now go through the lectures. So in MPI, MPI3 added these new neighborhood collective operations, MPI neighbor all gather, and the one I've used here, MPI neighbor all to all. However, they have MPI neighbor all gather V, MPI neighbor all to all V, and all to all W. And the reason is it allows you to do halo exchange with a single MPI call, as I've just illustrated with the benchmark. And so, well, this is the practical is to replace, if you have, this comes from an MSc course where we get students to develop a regular grid halo swapping code, and we want them to replace it with the neighborhood collective, but I've just given you an example here. Sorry, I'm losing the cursor again. So, you know, as I've said, if you have a 2D domain decompositive L by L array, you would split it up into P subdomains of size L over Px and L over Py, where Px by Py equals P. And the important point is, if you have an update, like a 5-point stencil regular grid update, where each point depends on its nearest neighbors, then that implies nearest neighbor communications. So that implies a 2D grid of Px by Py processes with halo swapping. It's slightly more complicated with unstructured meshes, but then what you have here is you end up with the communications pattern is represented by an undirected graph. So we have a more complicated communications pattern. So those are the two use cases: a regular grid halo swapping, which implies, in this case, a 2D grid, or a more generic unstructured problem where the communications pattern is represented by an undirected graph. And so MPI supports those through MPI cart create for the regular grid Cartesian topology, or for graph topologies. Now, the original graph creation routine was called graph create. They messed it up. They have other ones here. I'm not going to cover them in detail here because it's easier to explain for the Cartesian case, or easier to display, to draw the graphs, the pictures. However, it does generalize to general graph topologies. And so there's for Cartesian topologies, the way you find your neighbors with MPI cart shift, that gives you who our neighbors are up, down, left, and right. It's more complicated for a graph topology because you have to say, you know, who am I? You have to name how many neighbors are they and who are they, because in a graph topology, each process can have an arbitrary number of neighbors. But again, I'll focus on this more simple case, the MPI Cartesian case, where your neighbors, as we saw in the benchmark, were computed via MPI cart shift. So there's an example of topologies which comes from a tutorial. I'm not going to, So what we're going to do here is we're going to illustrate the use of MPI neighbor all gather. So an MPI all gather, basically everybody does a gather from every. So a gather is where a process, a root process, receives data from every other process. An all gather is where everybody does that. So every process in an all gather is receiving data from every other process. A neighbor all gather says every process receives data not from every other process, but from a subset of its neighbors. So every process chooses a gather from its neighbors. And there's an example here, which I'll go through briefly. It's slightly complicated because it does use graph topologies, but what it does is the way that the graph topology works is that you basically have to say for each rank who your neighbors are. Okay? So for rank 0, it says I've got 2 neighbors and they're 1 and 3. Rank has one neighbor, which is 0. Rank 2 has 3 neighbors, which is 3, 0, and 1. And rank 3 has also 3 neighbors, which is 0, 2, and 1. And that corresponds to this. I've actually got this graph here where you can see, for example, who are rank 2's neighbors. Well, they are, here it says rank 2's neighbors are 0, 2, and 1. Is that correct? Yes, 0. Sorry, I've got that wrong. Rank 3's neighbors are 0, 2, and 1. Rank 3 has neighbors 0, 2, and 0, 2, and 1. Yes. So the oh, I'm really sorry. I have clicked the wrong button. I'm very sorry about that. So let's go back to that. Thanks for pointing that out. So I'll just briefly recap. Apologies for that. I was saying here, MPI3 added these new neighborhood collective operations. MPI neighbor with the American spelling, all gather. The American spelling of neighbor, and the example is Halo Exchange with a simple single MPI call. I then covered how you might have this 2 use cases, and they are a regular grid where you want to split an L by L array across processes in a 2D grid, a PX by PY grid, or a more general case of an unstructured problem where you have an unstructured communication pattern where each process can communicate with an arbitrary number of neighbors, and that comes from unstructured problems. And in that case, the communications graph is the communications pattern is represented by a graph, not a regular grid. And typically these graphs are undirected. That means if A communicates with B, then B communicates with A. But the example here is actually a more general case. And so I said here that to create these topologies, you create Cartesian topologies with MPI can't create, and graph topologies have a number of ways of creating them, which have evolved through the history. And the way you create a graph topology is you basically say for every rank, how many neighbors does it have and who are its neighbors, i.e. who does it communicate with. So, and yeah, I've talked about these. So apologies, this was the graph I was showing, which wasn't making any sense. So for example, here, here we have a graph where each rank has a different number of neighbors and it communicates with a subset of them. And so what we're going to do is we're going to set up that graph in MPI, and we are going to then use that to instantiate that communications pattern. So so what we're doing is, if, for example, here it says if rank equals 1, then it has one neighbor, that's the degree, and it is 0. So if we look at that, it's that rank 1, it has one neighbor, yes, this is the outgoing neighbors, and it has 0 here, yes. So this is what the outgoing neighbors, it has 1. Rank 3 has 1, 2, 3 outgoing neighbors, and then 0, 1, and 2, and we set that up, yeah, 3 outgoing, 0, 1, and 2. So we specify that connectivity pattern through a couple of arrays, and then we do MPI dist graph create to create the graph. So basically, having done that, we can do an MPI neighbor all gather, and basically you will do a gather with all your neighbors, and the neighbors are specified by these lookup tables. It's quite a complicated example. It illustrates the entire. However, I'm going to use later on purely the Cartesian case because it is kind of easier and is what's illustrated in the benchmark. You'll see that when you do MPI graph create, there is an argument which is called reorder, and one of there were 2 design considerations for topologies in MPI right back in the early days. One was to allow you to tell MPI what your communications pattern was, and therefore to allow you to find out who your neighbors were easily. But the second one was, once MPI knows the communications pattern, in principle, it could remap your processes. It could say, well, David's going to do this communication pattern. The mapping he has of processes to physical processors is not optimal, and it can do a virtual remapping. I have to say, I would always so reorder equals true tells MPI it has freedom to remap the processes to try and attempt to get a more efficient mapping of your MPI processes to the physical processors based on MPI's understanding of the physical hardware and the network that machine has. I have to say, I don't think that I've never come across an MPI implementation that takes advantage of that. So, but in principle, imagine I'm running 256 MPI processes on 4 nodes, and each node has 64 CPU cores. There will be some default allocation of processes to processors, and it probably puts ranks 0 to 63 on node 0, 63 to 127 on node 1. But that may not be optimal. So, for example, if we have a 64 by 1024 array, we're going to create a Cartesian topology of each process has a 4 by 64. So we've got 64 by 1024 array on a 16 by 16 grid of processes. So each process has a 4 by 64. Sorry, the other way around. Apologies. We have a 64 by 1024 array. We want to have each process to have a relatively square subdomain of 16 by 16. And so we do a 4 by 64 distribution of processes. So our process grid looks like this. However, if we're on a 2D grid, each process communicates with its four nearest neighbors. And the problem here is the way it's worked out here is that the process ranked 0 to 63 on node 0, ranked 0 to 64 to 127 on node 1. An enormous number of messages go over the network. So what you would like is to have a mapping of processors to physical processes to physical processors or nodes, such that the maximal number of messages are kept within a node and don't go between nodes. Because of this slightly asymmetric distribution of the dimensions, we have a distribution where 128 messages are sent over the network from each node. Each node sends a message up and down in this first dimension, which goes to a different node. And so if you could renumber the processes, yep, Sean, you have a question? Yeah.
Sorry, it takes me ages to unmute.
Fine, yeah.
Sorry if you covered this already, but is there a way to make sure that to pin a certain rank number to a particular node?
So, so each node is a physically different computer with a different operating system. So when you launch your MPI job, there will be a default distribution of MPI processes to nodes. So if a process is launched within a node, it cannot leave that node, because that's a process under the control of a particular operating system. However, within a node, on ARCHER2, you will launch 128 MPI processes on each node. Within a node, whether those processes are physically bound to physical CPU cores depends on your system. On ARCHER2, they are. On some systems, they may not be. So that's kind of a hard. An MPI process cannot physically move from one node to another, because that would require an operating system moving a process between operating systems, and that's not possible. However, within the node,
sorry, go on. I was going to follow up. Which is the slurm parameter to set the number of ranks per node? Is it the number of CPUs you asked for?
So it's slightly how slurm is
NTASC, sorry.
Yeah. So on the way it's set up on ARCHER2, ntasks is the total number of MPI processes, and ntasks per node is the number per node. So you can do it from, I mean, you can specify the number of nodes and number of tasks per node, in which case the total number of tasks is inferred, or you can do it the other way around. You can specify the total number of tasks and the number per node, in which case it probably splits them up evenly. The problem is that Slurm works very differently on different systems, but there is, yeah, I mean, n tasks per node does tell Slurm system how many tasks to launch on each node. Does that make sense?
Yes, it does.
Now, you would normally make that the same as the physical number of CPU cores. Do you have a reason why you might want it to run fewer than so if I had 28 cores per node, might you want to run fewer than 128 MPI processes?
So the reason is I'm asking is because what is it? Usually, some of my colleagues, their idea is that they want to if they have a node with 8 GPUs on it, they want 8 ranks, so 1 rank per GPU, yeah. Somewhat. So is there a way to determine at runtime, you know, I'm rank number 0 and I'm running on the first node, and I'm rank number 1, I'm running on the first node, etc., etc. Or what's the sort of best way to do that pattern?
So you just want to find out what node they're on, not what CPU they're on within the node. Is that correct?
Yeah, basically, yeah.
Yeah. So there is in MPI there's a badly named function called MPI get processor name. Mm-hmm. If you called it now, it'd be called MPI get. That for each process tells you the host name. I mean, the reason it's called MPI get processor name is when MPI was defined, there was only every computer had a single CPU core. So get processor name was the same as get machine name. But anyway, nowadays it would be called MPI get host name or MPI get node name. But MPI get processor name is the function which gives you the character string which you would get from host name, and that lets you at least tell if they're on the same or different nodes. Does that make sense?
Yeah, that's exactly what I wanted. Thanks.
Okay, and I think, for example, if no, I won't do that. I won't show you the code because it's slightly complicated. But yes, MPI get processor name is yeah. So services can use internodal communication the same. No, so that's actually one of the exercises you look at in the ping pong benchmark. That modern processors are very complicated even at the node level, and you have non-uniform memory access. So I suspect that, you know, that so if you could run the ping pong on a ping pong on a single node, use 2 processes, then use 128 processes. And the way that the ping pong is set up is it ping pongs between the first and the last process. So in the first case, it ping pongs between processes 0 and 1, and they will be on CPU cores 0 and 1, right next to each other. In the second case, it will ping pong between processes 0 and 127, which will be at the 2 far ends of the physical process of the node. And I suspect you will see quite substantial. I expect very different latencies. So that was something you could do. So run on 2 and run on 128, and the ping pong code does actually print out where they are. It says, "Hi, I'm rank blah running on CPU blah of node blah." I think it does that. So that's something of interest to do, Seb. If you want to do that, that would be interesting. However, all that said, you don't really care because the internode comms is so much faster than going over the network. You're limited by the network the intranode comms, apology. The communication within a node is so fast, you're actually limited by the communications between nodes. So all that it's interesting. I think it's interesting, but it probably doesn't have a direct impact on your application performance. Does that answer the question, Seb? Sorry, I'm sure I pronounced your name wrong. Apologies. But that's an interesting test you can do. So this is just to go back. If you did a logical renumbering of the processes, you could basically come up with a distribution like this, so that many more of the communications were intranode versus internode. And this is this means that you have multiple identities. You will be ranked 0 in you might be ranked 73 in MPI com world and ranked 52 in MPI com cart, and that can be something of a software issue, but it's there. So your ranking com, oops, yeah. So the actually the reordering, that reordering is just a logical change of rank, and you have kind of schizophrenic identities within the same. You have multiple process IDs, multiple ranks within the same program. It might actually be easier to do the remapping at launch time, and so Slurm has many complicated options for doing the remapping at launch time. So you can do almost anything arbitrary, but it can be its default is just to line them up in order. So Seb, you were talking about physically for. Oh, sorry, you said inter. Sorry, I misheard you. Sorry. No, so you're right. Sorry. Yes, so ARCHER2 has a multi-stage network, and so yes, if the nodes are far apart, many hops apart, then it will be slower than if they're close together. So sorry, I misunderstood your question. You're absolutely right. That is true. However, you don't have any control over what nodes you're allocated, so it's not really useful. But it is true. Also, the overhead is surprisingly little because, as I said, the big overhead is getting the data into the network. Once it's in the network, it hops along quite quickly. So you're absolutely right. If you knew what the machine network topology was, and you had two nodes at extreme ends, then if you tried hard enough, you could measure an increased latency, maybe a decreased bandwidth between the two. But since you don't actually have control of what nodes you're allocated, it's not particularly useful information. Sorry, I misheard your question. So yes, you're absolutely right. It does vary, but you don't really. It's not something that's under your control. I think that Slurm tries to give you compact domains. It will try and give you nodes which are close together. So just to get onto the actual neighborhood collectives, they're in MPI4. They're called MPI neighbor all gather V, MPI neighbor all toward V and W. So MPI neighbor all gather sends the same piece of data to all neighbors and gathers one piece of data from each neighbor. That's not really a pattern which you would normally use. MPI neighbor all to all sends different data to each neighbor and receives different data from each neighbor. And if you think about it, that is actually the data pattern, the communications pattern for regular halo swapping. So that is why you can, with enough, if you do the setup correctly, use MPI neighbor all to all, as I did in the Halo benchmark for n-dimensional halo swapping. So I'll just go through these quickly. MPI neighbor all gather sends. It has a send buff and a receive buff, and it sends the same send buff to each outgoing neighbor and receives the equivalent, receives that data from what's incoming neighbors and sticks in order into the receive buffer. So it's quite a regular. I've never seen that pattern needed, to be honest. All gather V. It's a standard trick in it. Well, nomenclature in MPI. an all gather sends the same amount of data to every process. An all gather V takes a vector, a lookup table, and you can send different amounts of data to different processes. So it's slightly more flexible. So you have to specify not just the send count and the send type, but also the displacements where the data starts from and how much you're receiving. So it's slightly more general. You can send and receive data from different places. But again, each process is sending the same data to every neighbor, which isn't what you need for a halo swap. A neighbor all-to-all looks a bit better, that you send out different data to each neighbor and receive different data from each neighbor. But again, these are contiguous chunks. And that is not what we need for a halo swap. Neighbor all-to-all V allows you to send different amounts of data to each outgoing neighbor and receive different amounts of data from each incoming neighbor. But the problem is that all these blocks have to be contiguous chunks of data. And the problem with that is if you're doing multidimensional halo swapping in a regular grid, some of your halos are non-contiguous data because they're subsections of a multidimensional array. And so that's not enough. It gets all rather complicated, but this diagram, MPI neighbor all-to-all W, is the routine which allows you to do n-dimensional halo swaps in a general program, because it allows you to not only send different amounts of data to different neighbors, but it allows you to specify different types for incoming and outgoing data. And that allows you to specify, for example, if you have a 3D data set, to define MPI data types that correspond to the faces of that cube and send them out to all your neighbors. And so it is a slightly challenging prototype, but it does allow you to do n-dimensional halo swapping for a 3D grid with a single core, modulo a lot of setup which you've done beforehand. And so this is how it works. That we have to basically, if we want to do in a 2D grid, okay, we have a 2-dimensional array and we want to do halo swapping in both dimensions. We set up data types so that we're sending and receiving only one data type in each dimension, but we send the data types up such that the first data type is a contiguous data type, which is this one, okay, and the second one, so that's a contiguous type, that's a contiguous type, but the other halos are vector types which we have to initialize correctly. And then we basically have to say, well, we're going to send one data type in each dimension, but we have to say what the types are. Well, in the first dimension, they're contiguous. In the second dimension, they're a vector type. And we also have to specify the offsets. And this is where the displacements get slightly weird, because we have to specify the displacements in bytes. It's rather a complicated prototype, but it does allow you, after all this setup, to do halo swapping with a single core MPI neighbor all-to-all W. And so it is a relatively elegant routine, modulo the fact that you have to do a lot of setup beforehand. So there's a bit of a run through, but it does achieve that communications pattern, which is exactly the 2D halo swapping pattern that we wanted. So the summary is that topologies are useful for regular or irregular domain decomposition. You can look at replacing point-to-point communication with a single neighborhood collective. The one which you tend to use is MPI neighbor all-to-all W. And that actually allows, in principle, MPI to optimize the whole pattern of messages. Although if you look at the benchmark, it looks like actually in most implementations these days, the neighborhood collective is implemented with a whole bunch of non-blocking sends and receives. But it may be simpler to call the neighborhood routine than to do it yourself. So sorry, that was a bit of a run through. I thought quite a lot of. So I'm happy to answer general. Now tomorrow, I'm sure people need to get away at the end of the day. Just to Hopefully you can see the. Can you see the timetable? My sharing has been going a bit awry. Yeah, fine. So tomorrow, what I'm going to do is I'm going to talk about MPI plus OpenMP in the morning, and the afternoon I'm going to touch on the new. It's related to MPI plus OpenMP. So tomorrow is all about exploiting the shared memory nature of our compute nodes. I think the important point about MPI is it basically ignores that. MPI's view of the world is a whole bunch of processors, all of which are equal, but we know that processors aren't equal. Two processors might be on the same node and have fast communications and can share memory in principle. They might be on different nodes and have slower communication and can't share memory. So the question is, how do you take advantage of that in a real code? And what the answers are, there are two ways to do it. One is you can mix MPI and OpenMP, which is processes and thread parallelism in the same application, or you can use MPI's built-in shared memory model, and I'll cover them both tomorrow. So I'm happy. So there's clearly a bunch of very interesting questions there. Are there any other questions people had just generically about MPI? Or, I mean, if you have any, I'm here for the next 50 minutes. I'm happy to answer questions. If people had general questions about MPI, we had some interesting questions there from Seb and from Josh. Sorry, Sean. So UGE is what's UGE? I'm not. Oh, Unified Grid Engine. Okay. SunGrid. Okay, fine. This is so. Okay. So yes, this used to be called SunGrid Engine. Yes. So we used to run SunGrid Engine as it was called then. Now it must have been brought over by somebody on our previous system. So yes, I think. Yes, I think Slurm has more. It's more complicated, but it does have more system-specific options. It allows you to specify more in detail than SunGrid Engine or UGE does. So yes, that's my recollection. It is so. It's important to realize that MPI has a very virtual view of the world. MPI says there are a bunch of processes running on a bunch of computers. Okay, that MPI talks about process-to-process communication. It doesn't care if you're running 100 processes on a laptop or 100 processes on 100 nodes of ARCHER2. MPI talks about communication between different processes. How those processes are mapped onto the physical hardware is something which is really determined by your local configuration and the job launcher, such as Slurm. However, recently, these new features we'll cover tomorrow have allowed you to sort of say, well, at least are these two processes on the same node? Okay, so MPI still doesn't really care about whether they're on the same. Yes, so no. So the advanced collectives outside, if you clone the repo, you will get a bunch of slides which I've given in the past but not given anymore. So those are in the GitHub, but they're not part of the schedule. They were there from. That's why I said if you clone the Git repo, you'll get quite a bunch of random stuff. So I'm not covering the advanced collectives here. I used to, but I used to do that in preference to doing hybrid MPI OpenMP, but a lot of people said they were much more interested in MPI OpenMP, so that's why. But the slide deck's there, but I don't cover that. No, you haven't missed anything. It's just it's a hangover in my Git repo, but they're not linked in from the README. So that's my. Does that make sense, Josh? Yes. Yeah, so I think the advanced collectives is slightly esoteric. Well, I don't know. yeah, I like it. I think it's fun, but I find that people are much more interested in hybrid MPI and OpenMP than they are in the advanced collectives. Yeah, I mean, just to say what the bottom line is, let's just show, I mean, I think just to show you, I'll find us the slide if you give me a few seconds. So this is okay. I'm trying to. Okay, so so I'll share that. So this is from my MPI course. So it's like, so if you have a problem which has a large you have a one-dimensional problem. So you have a large vector, and you want to split it up into pieces across processes. So what you're saying is, I have a large vector, say A, B, C, D, E, and it's split across processes A, B, C, D. Each of these could be a big chunk, but you've got a large vector, and it's split up into chunks across. You're writing the process as being in a line. A nice thing to do is, if that data is on disk, is you read the data in from disk, and then you call a scatter. A scatter takes that line of data, and splits it up into chunks across processors. The first chunk goes to the first processor, the second chunk to the second processor, the third to the third, the fourth to the fourth, the fifth to the fifth. That all looks great. So scatter looks like a great routine. You've got a regular decomposition of your data, you read it in onto a particular process, and you scatter it out to other processes. Great. However, we tend not to do 1D problems, we tend to do 2 and 3D problems. It is surprisingly difficult to generalize this scatter to a 2D problem. So to do that, you need to understand in some detail how collectives and derived data types work, and that's what that lecture. It told you how you could use scatter to split up a 2D data set across a 2D grid of processes in 2D blocks. But the jump from the 1D to the 2D is surprisingly difficult, and it's slightly technical and involved. But that's what those lectures are there for, because a lot of people used to ask that. But it's not something I've seen so much interested in the past. Does that explain it?
Sorry about that. Yes, it does. Yeah, it's good to have the slides. I'll have a look through, because in
there are a couple,
one of the main codes I work with, I have exactly this problem where I have my data is logically 2D, and then I need to do a really big all-to-all.
Okay. Yeah.
But the issue is, I have a big all-to-all, and then some very load imbalanced computation, and then another all-to-all.
Right. What's the code? It's not
being, yeah, just a little bit. It takes a lot of time, and you just spend a lot of time waiting for the collective communications if you just use like a blocking all-to-all. So I'm kind of interested in this to see if we can speed it up in any way.
Right. So,
but I know that's not a common kind of workflow for most codes.
So why is it? So the common use of all-to-all is for transpose. Maybe doing Fourier transforms or something. I don't know if that's the use case, but you're saying it's load imbalanced.
Yeah, it is a Fourier transform as part of it, but then there's some extra computation. So we do we do an all-to-all, we do a Fourier transform, we do an all-to-all back again. So then we do an operation on each frequency, and that is very load imbalanced.
Okay, right.
Some frequencies have a problem that is solved very easily, and some frequencies have a problem that is much more difficult. So then once we've done that stage, and we do all the frequencies in parallel, then we do an all-to-all again, in SFFT, all-to-all again. So there's a lot of, there's 4 all-to-alls, but that middle section is very load imbalanced.
Okay. Okay. What's the application, just out of interest? It sounds, it doesn't sound like
It's a parallel in time method.
Oh,
So the
okay,
idea is
right.
if you want to solve lots and lots of time steps all at once. So if you do an FFT in time, you can then be doing work on every frequency in parallel. So then you do an inverse FFT back, and you manage to solve a whole load of time steps in one swoop.
Okay, fine. It's not an app. Okay, that's not an application. So that's not a use case I've come across before. So I think, yeah, okay. So the exercises show for gather and scatter, but they would generalize to all. Yeah. How the derived data types work, and there are solutions there for simple 2D grid problems. I think it's gather. I can't remember if it's gather or scatter I use, but there's a simple matrix problem which shows it does. Yeah, these things do get quite tricky. So you're doing the communication yourself and then calling a library FFT. Is that right?
Yeah. So I actually rely on so to do the communications, the all-to-all, it's a library MPI for pi FFTW that do it with all-to-all W.
Okay.
So they get the derived data type so that you get the like you don't have to do the rearranging yourself.
Yeah. Okay. Okay. But it's Python. You say it's Python at the highest level.
At the highest level, yeah. Then it's code generation. So everything that actually gets, like all the computation that gets run is C kernels. That's like automatic code generation. Yeah.
Right. Yeah. Fine. That's interesting. Okay. That does sound, yeah. So I said I mean I don't want to be down. Load imbalance is one of the hardest. But can you predict the load imbalance? I mean, you said it was frequency dependent. So do you have a heuristic for how it would vary with frequency? Or
yes. Yeah.
Okay.
Yeah,
right.
And we end up doing a lot of iterations. So even if I mean, I can almost always predict it, but we can always do the first iteration, and then just see which ones are the most difficult, and then that is constant throughout the run. But yeah, some of them take like 10 to 15 times more iterations than the easiest frequency, as it were.
So it's not predictable, but it's repeatable, is what you're sort of saying.
It is.
Okay.
So it is almost always predictable, but it is always consistent over a single run. So in the cases where it's not predictable, you just do one iteration and then check which ones are difficult.
Okay. And so what do you actually hope to, sorry, I was lost of that. So what do you actually hope to improve? So you're saying that the all-to-all takes a lot of time because...
So the all-to-all takes a lot of time because it's all-to-all, but then straight away, then straight away after that, you end up doing a very load imbalanced computation. So I was wondering if there was any way to kind of use some of these kind of more advanced collectives to maybe do the gather scatter explicitly for the hardest frequencies, like the frequencies that take the longest, and then do an all-to-all. And then do an all-to-all on like a smaller communicator for all the easier ones, because it tends to be like 80% of them are fairly easy and 20% of them are fairly hard.
So what machine are you running on? I mean, that might be again, all-to-all is very tough on the network and its performance is quite hardware dependent.
We're on ARCHER2 at the moment.
So and you're using the Cray, you're using MPI for pi from the Cray Python, I guess. Like
we link into the Cray MPICH.
So there is a performance issue with all-to-alls in the default MPI, but you can you can improve that. We can maybe chat about. Are you going to be able to attend tomorrow? I don't know if you.
Yes, yeah, I will be.
Would you be able to turn up like 10 minutes early or something?
Yeah, sure. Yeah, absolutely.
I mean, it might be a long shot, but there is. You might actually be doing something which is actually largely possibly a slight failing in the MPI library rather than your code. There is a couple of things you can tweak, which you might get a freebie, is what I'm trying to say. So if you I'll try and be there early, maybe 10 minutes early tomorrow, and I can just talk you through it. It might be a no-go, but it might help. As I said, you might. I'm not doubting you have a problem, but it might be something which is actually an inefficiency in the MPI library, and the problem might be exacerbated by that. Is what I'm trying to say. It very much depends on the details. But yeah, okay. But it's very simple to test. That's a simple thing to test. A couple of runs, and you should be able to see it. Okay, I'll speak to you maybe earlier tomorrow. It's Josh, was it? Okay, so
yes.
I'll speak to you. I'll try and speak to you maybe 10, 20 past 9 tomorrow morning. Okay, cool. Okay.
Yeah, that'd be great. Thanks.
So I also said I don't know if Adeleki is still around. I don't know. Do you know how to get the screen sharing working? Or maybe Adeleki still is. Yeah, so we could try a different. I'll set up a Zoom call. I'll send you. What's your email? Can you give me your email? Actually, I could get it from the registry. But if you could just type your email, actually, well, if you don't mind typing your email in, or otherwise I'll get it from the. And we could try a Zoom call. That's normally more forgiving in terms of screen sharing. Oh, just for everyone else, thanks for coming. I'll see you at 9:30 tomorrow morning, but we'll do MPI+OpenMP. But okay, fine. Okay, so speak to you all tomorrow, and I'll dash off and maybe do a Zoom call with.
Thank you.